Okay. Yes, absolutely. You are going to have a quiz, right? It's been on the board all week, and the checklist has been up for half the week, so that's what you're going to have. But for the first 40 minutes of class, for the first 35 minutes of class, we're going to try something a little bit new. I'm not going to lie, when most of you yesterday were in the Hall of Fame ceremony, I tried to get the grade 11 students to teach themselves how to do what we're going to be doing today. So I will be interested to see how easily this concept was learned yesterday.
You're actually so funny. Like, I've never laughed at you so hard.
You've never laughed at me so hard?
Yeah, because I did
At
nothing.
me?
Yeah, because I did nothing.
Oh, okay.
I'm actually going to be serious with you. I did nothing.
Yeah, I know. Yeah.
Yeah, you should know that.
Yeah, I know. I understand now.
Good.
I get that. Okay. Yeah, they are taking advantage of me. I want to draw an analogy, and the analogy that I want to draw is back to our equilibrium unit when we tried to predict Bronsted-Lowry reactions. Do you remember how to do that? If I said you have ammonium chloride, and I'm mixing it in with sodium hydrogen carbonate, and then that's fine. So I've got a solution of ammonium chloride and a solution of sodium hydrogen carbonate. Do you remember when I wanted to predict the Bronsted-Lowry reaction, do you remember what the very first thing we had to do was? Maps. We had to list the major entities in the solution, right? Because maybe this isn't an acid or a base, maybe that's not an acid or a base either, maybe water is the only acid or base, right? So we have to list our major entities in solution. Okay, ammonium chloride, what is that going to stay together or split apart, or what's going on? Is it going to split apart? It's ammonium. It's an ionic compound, and it's got really high solubility, so it will split up. So we're going to have ammonium, and we're going to get chloride. Okay. What about sodium hydrogen carbonates? Is sodium hydrogen carbonate going to stick together or split up?
Sodium.
Yeah. It's going to be sodium, and it's going to be hydrogen carbonate. Perfect. And then, what else? Water. That's super important for us to understand for this and for the predicting redox reactions. Is everything okay? No, not everything is okay? Uh-oh. What was the next step? Sophia. Finding the strongest acid in the strongest base. How did you find the strongest acid in the strongest base? It's just in the data booklet, right? The strongest acid, is that located top left or top right? Bottom left or bottom right? Top left. So whatever is the highest in your list of acids. So what's the highest acid we have here? Let's go from the top. Do we have hydronium? No. Do we have oxalic acid? No. Do we have sulfuric acid? No. Do we have hydrogen sulfate? Do we have phosphoric acid? No. Do we have nitrous acid? Do we have any of these things? No. Yes. We've got ammonium. Even though it's super far down on the list, ammonium is our strongest acid here. So we've got ammonium. This is our strongest acid. And then what's our next strongest, what's our strongest base present here? We've got HCO3, and because we're starting from the bottom and we're working our way up. So that's important to understand that we're basically starting on this side, working our way down, starting on this side, working our way up on opposite sides of that chart. So this is our strongest acid, and this is our strongest base, and then we react them together. We're basically going to do the exact same thing for predicting a redox reaction. What's the first thing we're going to do when we predict a redox reaction? We're going to list the major entities. And then we're going to find, instead of the strongest acid and the strongest base, what are we going to find?
Strongest oxidizing.
The strongest oxidizing agent and the strongest reducing agent. Is that okay? So that's the idea behind this. Perfect. Redox reactions are 50% oxidation and 50% reduction, so we need an oxidizing reaction and a reducing half reaction. Please remember that the number of electrons lost must equal the number of electrons gained. If something loses 2 electrons, if something loses 2 electrons and something else gains 5 electrons, can this thing lose the same number as this thing gains? Not the way it is right now, right? So we have to change these, right? We have to multiply this thing by 5 and this thing by 2. What's that called? We're getting the lowest common multiple. So it's important for us to recognize that. Okay, reminders, ionic compounds must be dissociated. Leave polyatomic ions alone because they don't break up in solution, right? This hydrogen carbonate, we left that alone. That's going to stick together. It doesn't break up into hydrogen and carbonate. Yes, acidic solutions contain hydronium. I understand that, and I totally appreciate that. But to simplify things, we say like acids, they just produce hydrogen ions. Is that okay? Yeah, I understand this hydronium, but hydronium is just a water with a proton attached to it. And then water is always present in solutions. Perfect. Here we go. Here are a list of instructions to predict redox reactions. Same thing we just talked about. List all entities. Choose the strongest oxidizing agent. Choose the strongest reducing agent. We have to write out the reactions, though. And then based on the half reactions that we write out, then we can balance it using the electrons. This is the most key. I don't want to say most key because you have to do all of them properly. But this is the one that people, they kind of forget sometimes. Balance the electrons by multiplying each equation to get the lowest common multiple and add it together and get a net ionic equation. Use the spontaneity rule to predict if it's spontaneous or non-spontaneous. Let's try this out. A copper 2 nitrate solution mixes with aluminium metal. Hello. So, copper 2 nitrate. When I put copper 2 nitrate in water, what are we going to get? We're going to get copper 2 plus. So we get, from copper 2 nitrate, we get copper 2 plus ions. What else do we get when we put copper 2 nitrate in water? Possibly we get nitrate. I can't stress enough how important it is to have these charges on here. People love to split up copper 2 nitrate into copper and nitrate. And this tells me you have copper, elemental copper, right? With no charge. That's bad. No bueno. Please don't do that. You have to have the charges on the ions. Okay, it mixes with aluminium metal. What does aluminium metal look like? Shiny. Shiny. Perfect. Thanks. But how do we indicate it? Al 3 plus. Elemental metals they do not have an ionic charge, right? Right? It's just atoms. All elements, if it's an element, if I just said you have aluminium, you have elemental, so just atoms. They haven't reacted to turn into ions yet. So we have Al solid. And what else do we have in our mixture? Water. I think for some people this is going to be the hardest step. For some people, getting the charges properly, figuring out what is actually in here, that's the hardest step. Okay, well, these are our major entities. What's the next thing that we have to do on our checklist? Choose the strongest oxidizing agent. Let's identify the strongest oxidizing agent on page 7 of your data booklet. Yeah, and if you can't read that way over there in the corner, maybe you just take out your data booklet and follow along with me, right? Okay, where do we want to find the oxidizing agent first. Is that okay?
Yeah.
So let's find the strongest oxidizing agent. Where do we find all the oxidizing agents? On the left-hand side. How do we know that the oxidizing agents are on the left side? Because it's a reduction half reaction. They're all gaining electrons, right? Okay, stop me when you see something that we have in our solution.
Yeah, sure.
The very bottom.
No. Doesn't NL through though.
Okay, let's. All right, this is good for us to go through. We all know, we don't have any fluorine, we don't have any lead oxide, we don't have any permanganate, we don't have any gold ions, we don't have any perchlorate, we don't have any chlorine. Do we have nitrous acid? No, we don't have I know it's got NO something, but we don't have that. Okay, dichromate, no. Oxygen, manganese dioxide, bromine, mercury. This thing, no. No. No, it's not oxalate. Hypochlorite. Hypochlorite. Holy guacamole. Okay, this is really important. Do we have any of this?
Yeah.
Yes. Do we have any of the thing that's required to react with it?
No.
No.
H2O.
Yeah, we have H2O. But we don't have hydrogen ions.
Perfectly fine.
Okay, so keep going. If we have one of these, but we don't have that, we got to keep going. No. Yes. Copper 2 ions. So copper 2 ions are our strongest oxidizing agent. Now let's identify our strongest reducing agent. Where do we find the strongest reducing agent? The bottom on the other side. Do you see how it's very similar to your acid-base table? Coming from opposite, whatever. Okay. Stop me when you see something that we have.
Jesus.
Oh man. We have this as the strongest reducing agent. Good. Holy cow. So, what we have to do is we have to write out the half reactions of these things. But I need you to understand, we can't write out 2 reduction half reactions. We have to write out 1 reduction half reaction and 1 oxidation, the other one. Oxidation half reaction. Hopefully, it kind of makes sense. The copper 2, because we're starting with copper 2, we will just write this reaction the same way it appears here. We're starting with this thing and we're going that way, right? But with the aluminum, we're starting with this thing, so we have to go that way. So I would flip this reaction, turn it into an oxidation half reaction. So let's try that. Copper 2 plus gains 2 electrons. And I'm not going to use equilibrium arrows anymore. I'm just going to use quantitative arrows. So that turns into copper metal. This is my reduction half reaction. What's my oxidation half reaction going to be?
Aluminum ion.
It's going to be aluminum metal. Why are we starting with aluminum metal? Because that's what we have, and we have to turn this into an oxidation reaction. So we have to take these and flip them, right? So we have the aluminum metal turning into aluminum ions, and it's releasing 3 electrons. Yes, sir.
Is it a cardinal sin to write aluminum ions first?
Yes.
Is it a cardinal sin to write aluminum ions what?
First. Like,
Oh, big time.
really?
Yeah. Okay, why is it a cardinal sin? Why is it going to be a cardinal sin to write it like this? What I want to know. What I want to know is if we add these reactions together, right? What's the lowest common multiple between 2 and 3 electrons? 6. So we're going to have to multiply the top reaction by 3 and multiply the bottom reaction by 2. But when I do this, I'm going to get 6 electrons on the left-hand side plus 6 electrons on the left-hand side. The electrons can't cancel each other out. Do we have something gaining electrons and something else losing electrons here? Here?
No.
The way it's written here? No, we don't. You have to have something gaining electrons and something else losing electrons. Is that okay? Yeah, that's why. Okay. So we've identified that the lowest common multiple is 6 moles of electrons. So we have to multiply the top reaction by what? 3. That means everything in that half reaction gets multiplied by 3. And we have to multiply the bottom half reaction by 2. Now let's add it together. The first thing I want to say is that this 3 again gets multiplied to everything in this half reaction. So we get 3 copper 2 ions plus 6 electrons, and that's going to give us 3 copper metal atoms. Some of these might get really long.
Great.
Like we're going to get really big long reactions, but it'll be okay. Okay, what else do we have on the left-hand side of this reaction? We're adding our reactants with our reactants, so we need 2 aluminums. Yeah. What? Oh, well, I left space. Why didn't you leave space? Put the aluminums down here, boss. It's fine. Okay, what else do we have in the products? How many? 2 aluminum 3+ atoms, or ions. And how many electrons? 6 electrons. So here we have, we're gaining and losing the same number of electrons, so what can we do with that? We can just cancel out the electrons. But that's the goal. That's the goal of a redox reaction. Is as long as something is gaining and losing the same number of electrons, then we're fine. Okay, let's write the net reaction now. 3 copper 2+ ions react with 2 aluminum metal atoms. And they're going to give us 3 copper metal atoms and 2 aluminum 3+ ions. Does this bottom equation follow both of our laws? Yes, it does. Perfect. 3 coppers, 2 aluminums, 2 aluminums. What's the total charge on the left? 6 positive. What's the total charge on the right? 6 positive. Good. Are we okay with that? Kind of. Did we start it the exact same way that we started predicting Bronsted-Lowry reactions? Yes, we wrote the major entities and we identified the strongest something and the strongest something. And then instead of just directly reacting them with each other, we wrote down the two half reactions, and then we had to find the lowest common multiple, and then we had to cancel out the electrons, and that's all we have to do. What? Oh, yes! Oh man, I got so focused in the details that I didn't actually identify if this was spontaneous or non-spontaneous. How can you identify if something is spontaneous or non-spontaneous? Uphill or downhill, right? Is this uphill or is it downhill?
Downhill.
The copper 2+ is way up here and the aluminum is way down here. It's so far down there you can't even see it. So this is a downhill reaction. It is spontaneous. It will go forward. Perfect, thank you. Yes, comma, spontaneous. That's a proper sentence in chemistry.
So for the written portion on the math diploma, they're really picked for the written portion. Are they the same way for the Chem 31 as well?
No, because there is no written portion for chemistry.
Okay.
Wait, actually?
Are you serious?
Did you not know that?
There's no written.
There's no written portion. It's okay. Let me be very clear. On your chemistry diploma, you will have. On your chemistry diploma, you will have 44 multiple choice and 16 numeric response questions. Yes, for a total of 60 questions. Typically, you are given 3 hours, right? That is 3 minutes per question, but everybody gets double time. So you are technically being given 6 hours. Please, for the love of God, do not take 6 hours to write your diploma. Why would you? I mean, for some people, yeah, for some people, taking 6 hours is like a reasonable thing. That's borderline unreasonable in every circumstance. But for most normal people. No. Like for most average people, like, okay, I'm gonna say something. I'm gonna say something, and I'm gonna tell you why for most normal people. Okay? No, calm down. It's not derogatory. Calm down. For most normal people, their brains cannot function at a high level for 6 hours. I know mine can't. My brain cannot function for a high level for 6 hours in a row. So in order for me to actually take all 6 hours, what I have to do is I have to write for 3 hours, take a nap for an hour, write for another hour, take a nap for half an hour, and then write for another half an hour. But by then, I'm losing rhythm. I'm losing sense of which questions I thought were difficult and which questions weren't difficult. What you have to do is you have to think about at what point am I no longer being productive on this exam. The vast majority of us are not going to get 100% on this diploma exam, and that's just the reality, and that's okay. The standard is not 100%, but the standard is for you to be able to judge when you are okay with what you've done, with the product that you've been given. So, anyways, that's why I say normal people. Most normal people can't function for 6 hours in a row writing a diploma exam.
The math diploma, the math 30-1 diploma is 9 hours. You have 9 hours to write it.
I was unaware that it was 9 hours. I mean, is the multiple choice numeric response and the written, are they all at the same time?
Yeah.
You take naps during like flex?
What?
You take naps?
I take naps during flex? No, I will admit, when I'm teaching, Yeah, but when I'm teaching, my brain isn't functioning at as high a level as a diploma exam requires, right? It's functioning at a pretty high level, but I'm not operating at max
Well,
capacity.
it's not functioning.
I mean, that's why I forgot to do spontaneous, non-spontaneous. My brain's half in it right now.
You need a smoothie.
Yeah, I need another smoothie. Okay, let's try another one. Talissa, or somebody, can you just close that door? It's getting crazy out there. Boston, tell me what to do.
We're talking about science right now.
Okay, well, look, check the checklist on the previous page. Or, no, sorry, check the checklist on the top of the page.
List all identities.
Okay, let's list all of the major entities. Sure, let's try that. So, potassium permanganate, is that an ionic compound? Yeah, then split it up. What does it get turned into? Potassium ions and permanganate. What is permanganate? MnO4. Okay, what else do we have? It mixes with acidic tin chloride. So what do I have? I've got tin 2 plus, right? SN2 plus. What else do I have? Chloride. What else do I have? Water. Don't we have what, Max? Hydrogen ions, right? Where do we see hydrogen ions in here? Acidic. We have acidic.
Okay, I get it.
Calm down. So now we have acidic tin 2 chloride. But what that means is the hydrogen ions can go anywhere. It doesn't matter. We're just listing them, right? So let's look at our list. Stop me when you find something that is really high up on the oxidation agent list. Stop me.
Stop.
There you go.
We have permanganate and hydrogen ions, right? We have both of those things. So what I will say is that the hydrogen and the permanganate, they combine to be our strongest oxidizing agent. Now let's write, or let's identify our strongest reducing agent. Where is the strongest reducing agent supposed to be located? Bottom right. On the bottom right. So again, stop me when we have the strongest reducing agent. Boom.
Stop.
Boom.
What?
Yeah.
Oh,
Right? Do you understand why it is so critical to have your charges appropriately labeled? Do we have potassium metal? No, we don't. My voice is starting to go sour. We have potassium ions. Yeah. I just gotta stop curving, that's all. Let's try this. Let's keep going. Anything yet? Anything yet? Anything yet?
No, it's like stop. No.
Yes.
Oh, yeah.
Yeah, we do.
Oh, hey.
That is yes.
Tin ion.
No?
Yes.
We have it.
Why? Why?
I was waiting for the gears to kind of link in with each other for some people's brains, that's all. Yeah. Okay, so this is the strongest reducing agent. My voice is going to crack so hard here in a little bit.
I can speak for you, Walton. Write me down like.
Mr. Zakowski was telling me about one day his voice was so bad that he just pulled up like a text to voice app or something, and he just typed in everything he wanted to say. So it was this weird Stephen Hawking voice, and it was like, "Hello, children," that kind of thing. But I can't type that fast.
Scary.
Yeah, I know. So what do we got to do now? We've labeled our strongest oxidizing agent. We've labeled our strongest reducing agent. What do we have to do now?
Write the reactions.
We have to write out both of the half reactions. So let's write out our reduction half reaction. Let's write out our oxidation half reaction. Which one of these is our reduction half reaction? It's the acidified permanganate, right? So we've got MnO4 minus plus how many protons?
5.
Because there's 5 electrons, right?
Oh,
Yeah. Oh, okay, we're kind of a step ahead.
Yeah. And then what's this going to make? Manganese 2 plus and 4 H2O liquids. Can you understand why this is going to take up a lot of room? Yeah, this is a long half reaction. We've got a short half reaction coming up as well.
Doesn't look very.
So, how can you tell? How do you know if I were to give you this reaction? How could you tell from a mile away that this is a half reaction?
because electrons are being added.
You see electrons anywhere in here. That's what makes it a half reaction. It's showing you that this stuff is gaining 5 electrons. That's a half reaction. Okay, so our SN2 plus, are we going to write it the same way we have it right now? No, we got to flip it. So our oxidation reaction is SN2 plus is turning into SN4 plus 2 electrons. So can we just add these two half reactions together?
Yeah, balance it.
What do we have to do first? Balance the electrons using the lowest common multiple. Good. What's the lowest common multiple between 2 and 5? 10. It's 10. So we're going to multiply this reaction by 2, and we're going to multiply this reaction by 5. Go ahead and do that, but common mistakes are that you multiply all the reactants, but you forgot to multiply the products, right? That's a really common mistake. So go ahead and try this out. This is a long reaction, I agree. It's not the longest reaction we will do.
Is it going to be 2 of those like really long boys?
Yeah, it'll be 2 of those really long boys, yeah. So for example, we could get the permanganate reaction, but then we could get hydroxide and sulfite together. That would be another one. Okay, hopefully you get as a as a completed reaction. Hopefully you get and I'll show you a shortcut. Hey, do 10 electrons, are they going to cancel out with 10 electrons? Yeah, so you can just cross them out right now if you want to. As long as you know they're going to cancel out.
last week of October.
Okay. Hopefully that's your net reaction. What I want to do is I just want to double check. What do I want to double check before I do spontaneous or non-spontaneous? What do I want? The two laws, right? So I'm not going to do the law of conservation of mass right now. That's just too much stuff to do. But we can do the law of conservation of charge. -2 plus 16 is plus 14. Plus 10 is positive 28. So we got to make sure this adds up to positive 28. Positive 24. Positive 24. -2 plus 16 is 14. 14 plus 10 is 24.
Yeah.
Perfect. Okay, good. We've got 20 and 4, so 24. Not bad. Is this spontaneous or non-spontaneous?
Spontaneous.
This is spontaneous. Why is it spontaneous?
Down.
This is spontaneous because our oxidizing agent is higher up than our reducing agent on the list. Yeah, so it's downhill. Good. Do you feel confident doing one by yourself?
I don't want it. It's too long.
I don't see why not. Go do it right now. Yeah, and then after this question-ish will be the quiz, yeah. I should move the quiz to Monday? I'm sure not.
Okay.
Yeah.
It was worth a shot.
Yeah, it was.
Double check, don't. I'm writing it down for now.
Okay. This should be just by yourself. You don't, okay. You have a data book with the right beside you under your left elbow. Do I have to open it and see? I don't know, just tell me. I'm going to stop you in about 30 seconds, and we're going to make sure we all have the same major entities, and then I'm going to let you go after that.
Where's your water?
Matthew.
It's actually potassium plus.
Good. This should be potassium positive, right? Like I'm intentionally putting in at least one mistake to make sure that we're all kind of spotting these things. And so potassium plus and what, Alina? Water. And also water. Matt.
When you're finding the SOA,
Yeah.
so you find all the entities are right, so about like the right mass number or something, is that fine?
No, that's fine. Remember, when you're listing the major entities, this says nothing to do with how much there is of each. It just says you have this lots of this, you have 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 lots of that. So, Max, there's plenty enough of all of these things to make whatever combination you want.
This is a long one.
Yes, it is.
Which iron?
It's iron 2 plus. Iron on this one. It says 2 plus. Iron 2 plus is the strongest.
O2 plus, is it 4H?
Yeah.
4H plus 2. Oh,
Because we don't have anything lower than that on this.
Okay.
So there's no other combination. That's what it is.
Gas. This can be. Can I just times the water by 3? Can't I just times this one by 3 since there's 6 up here? We don't like it. Okay.
Okay, what's our strongest oxidizing agent? So that's the acidified dichromate, right? What's our strongest reducing agent?
Oh, wait. Oh, I missed it.
Yeah. Is it pretty easy to miss something on this list? If you don't actually go line by line from the bottom to the top or the top to the bottom, it's pretty darn easy to miss one of these. What? I don't know. This is fine. This is good the way it is. No, but if you missed iron 2 plus, the next highest or the next strongest reducing agent would have been water. And so you would have reacted acidified dichromate with water, which would have been the wrong reaction.
Oh, it's everything.
So we're going to get our Cr2O7 2 minus plus, what is it 14 hydrogens? Plus 6 electrons. Turns into 2 chromium 3 pluses, yeah. Plus 7 H2Os. And then our oxidation reaction is just Fe2 plus turns into Fe3 plus an electron. So what's our lowest common multiple? 6 electrons. So I just have to multiply this by 6. So I'm going to get Cr2O7 plus 14 hydrogens plus 6 iron 2 pluses. The electrons cancel out. So we're going to get 2 Cr3 plus aqueuses, 7 waters, and 6 iron. Good. So our left side is 12 and 14 is 26, minus 2 is 24. And then our right side is 6 and 18 is 24. So good, we're fine. Is this spontaneous or non-spontaneous? This is a spontaneous reaction, right? Yes, spontaneous. Good. No, we're gonna talk about disproportionation on Monday. Disproportionation on Monday. Good.